In our class for Chapter 2, the last slide we discussed was classification of fixed costs, where we classified fixed cost into what we consider committed fixed cost and discretionary fixed cost. Now that we've been exposed to the different types of cost, let's go through a cost behavior exercise. Uh, in this case, the company is called Duo Ball. It produces tennis balls. Each ball is considered a unit of production. Based upon the information provided below, provide a sketch of the cost behavior, in other words, a cost graph between a volume of 0 and 10,000 units. And 2, identify the cost behavior as a step cost, a variable cost, a fixed cost, or a mixed cost. So let's go ahead and take a look at the first item here. The first item is a rubber used to manufacture the tennis balls. And right now we know the rubber cost is 50 cents per tennis ball. Now, what you need to do is identify or do a very quick sketch of what you would consider that cost curve to look like between 0 and 10,000 units. And then secondly, based upon what you sketched in that cost curve, determine the cost behavior. It is a step cost, variable, fixed, or mixed cost. So at this point in time, you'll want to stop the video, come up with your answers, the graph, and the name of the cost, and then when you're ready, restart the video for an explanation. So go ahead and stop the video. Okay, in restarting the video now, if we take a look at the cost behavior in terms of 50 cents per tennis ball between 0 and 10,000 units, what we see is a graph that looks like this. And we start out, if we produce 0 units, there is 0 cost. And as we produce additional units, there's an additional 50 cents with each unit that is produced. So we get to 2,000 units, and 2,000 units times 50 cents a ball is 1,000. We go to 4,000 units, 50 cents a ball is 2,000. 6,000 units, 50 cents a ball is 3,000, and so on. So we can depict the cost curve right here as we see it. Now, under these conditions, again, if we remember cost behavior, we would call this particular cost a variable cost. Okay, so that's it regarding basically for this particular example. Now let's take a look at the next slide, and the next slide will be talking about the concept of depreciation. Now there's some type of depreciation on the plant, and it's being or on the manufacturing facility, and it's being recorded at $2,000 a month. Now again, what you want to do is, number one, provide a sketch of the cost behavior of the cost between a volume of 0 and 10,000 units. After you've done that sketch, based upon that sketch, identify the cost behavior as step, variable, fixed, or mixed. So again, go ahead, stop your video. When you're ready for the answer, go ahead and restart the video again. Okay, now we see the graph of depreciation at $2,000 a month, and you'll notice between 0 units produced all the way through 10,000 units produced, that cost remains the same. It's a flat line across all levels of production. So in this particular case, that type of cost would be considered a fixed cost. Okay, now let's go on to the cost of electricity. Now, in this case, we see electricity cost is going to be $500 per month. That's like basically electrical meter hookup and service fee. Whether you use the product or not, you're still going to pay $500 a month. You're also going to pay for the amount of kilowatt hours you're using in terms of manufacturing. And what cost accounting has determined is that the cost of the electricity in running the machines comes up to 10 cents per ball or 10 cents per unit of volume. So every time we make a ball, we incur at least 10 cents worth of electricity. So again, provide a sketch of cost behavior between the volume of 0 and 10,000 units. And number 2, identify the cost behavior as step, variable, fixed, or mixed. Go ahead and stop your video, do your sketch, ascertain the cost behavior. When you're ready, restart your video again. Okay, now we have a pictorial, or a graph of the cost. Of the cost behavior between 0 and 10,000 units. And you'll remember at 0 units, we still are going to incur a cost of $500 because we will pay $500 per month whether we use any type of electricity or not. Therefore, it starts out at $500, and then as we start producing units of the tennis balls, it starts going up by 10 cents for every unit produced. And if you take a look at 2,000 units, it's going to be approximately $700. If we use 4,000 units, it's going to be approximately $900 and so forth. But you can see it starts out at the level of 500 and then increases in basically a straight line up through the volume of 10,000 units. So in this case, when we take a look at the cost behavior for this particular cost, we would classify this as a mixed cost. Okay, the last item is supervisory salaries. Now, let's assume that a supervisor gets paid $5,000 a month. That's their salary. And we also know that a supervisor can supervise a sufficient number of employees to produce 4,000 tennis balls or 4,000 units. In other words, produce a volume of 4,000 units per month. Anything above 4,000 units, and we have to hire some additional employees, but we also have to hire a second supervisor to supervise those employees. So with this information in mind, again, let's provide a sketch of the cost behavior, again, between 0 and 10,000 units. And number 2, identify the cost behavior as step, variable, fixed, or a mixed cost. So again, go ahead and stop the video. When you're done with your cost behavior sketch and what you've labeled that cost behavior as, go ahead and restart the video. Okay, now we see the supervisor cost per month, and you'll notice between 0 units and 4,000 units, what happens is that we have one supervisor employed, and that's our 5,000. Then we skip to a production level above 4,000 units, which means we have to hire an additional supervisor. So now we have 2 supervisors between the volumes of 4,000 and 8,000 units, and 2 supervisors times 5,000 each equals $10,000. When we reach 8,000 units, we reach the next plateau where we need to hire another supervisor to supervise the workers that are going to produce the additional volume beyond 8,000. So we have a third supervisor. So now we have 3 supervisors at $5,000 each for a total of $15,000. So in this case, if we take a look at the cost behavior, what we understand is that these are what we call step costs. And that's the end of our cost behavior exercises. Now we need to look at the uniqueness of a mixed cost. Variable costs are pretty easy to discern because we simply identify the variable cost and we multiply it times volume. That's our total cost. Fixed costs are fixed costs, so no matter what the volume is, that's what the cost is. But we have this additional type of cost called a mixed cost, and it's kind of a hybrid. It contains both variable cost components and fixed cost components, similar to that electricity example we used in the previous exercise. Now, when we're taking a look at mixed cost, or cost of let's say a cost center or an activity where we know there's both variable and fixed cost, there are methods of estimating those fixed and variable cost components. And we're going to look at three of those methods. The first one is what we call the high-low method. The second one is what we call a scatter diagram. And the third method is what we call least squares regression analysis. So let's start off with the high-low method first. Now, here we have a situation where we have 12 months of data. We have the number of units produced during that month for whatever product it is. It's a volume. And we have the total cost of producing those units. And this total cost is composed of both variable and fixed costs. So the question is, how do we separate those costs from each other? Well, the high-low method is one of the ways of doing that. And basically our first step is to identify basically the highest and lowest points of production volume. So we take a look at the units produced at the various months, and what we're going to see is that the lowest point of production is in February, and the amount of units produced was 17,500 units at a cost of 20,500. We can see the highest point of production volume was in October, and that was 67,500 units at a total cost of $29,000. Now we're going to use this data to discern, basically to factor out or create the variable cost. So here's how we do it. Okay, step number 2, again, compute variable cost. VC stands for variable cost. Compute variable cost per unit. Okay, the first thing we notice right away is that in terms of total cost, at our highest volume level, our total cost, again within that circled area in October, is $29,000. We compare that to the total cost associated in the lowest month, which we've also identified, of $20,500. Now we take the difference between the two, and it means there was an $8,500 change in total cost between the highest point and the lowest point in this yearly production. Okay, now with what we do is now we take a look at the units of produce. We do a similar analysis. We start out with the highest level of production, which is the $67,500. So we subtract away the lowest level of production, which is $17,500. And in this case, the $67,500 minus the $17,500 means we had a 50,000 unit change in volume between the high point and the low point. Now what we do is we simply divide the 50,000 change in volume into the $8,500 change in total cost. When we do that calculation, we come up to, in this case, 17 cents, 0.17, 17 cents variable cost per unit of volume. So that is the variable cost component of our total costs. Okay, now that we have the variable cost, we have to basically discern the fixed costs. So step 3, we're now going to compute the fixed cost associated with these costs here. And this is a fairly logical calculation. The first thing we're going to do is we're going to take our basically our total costs of $29,000, and those total costs are going to equal, and I'm using, by the way, when I say $29,000 in total cost, I'm using the highest point of production. I could have also used the lowest point, but I just chose the highest point. So we have $29,000 of total cost in October. Now what we're saying, that's our total cost. So what we do now is we plug this information into our cost model. And so we take our variable costs times our volume plus our fixed cost is going to equal our total cost. So when we plug in the information that we just gleaned with the 17 cents in variable cost, we take 17 cents variable cost times the volume of that month, 67,500. So based upon that then, what's ever remaining after we do that computation is going to be the fixed costs. So what happens here now is if we break this formula down a little bit further, it's now $29,000 total cost equal, at this volume of 67,500, equal variable cost of $11,475. And in effect, algebraically, the remainder are our fixed costs. So what happens is that we solve for FC, and our fixed cost in this case happened to be $17,525. Now, so based upon this high-low method, we can compute our total cost, our mixture of variable and fixed costs at any level of production. Let's take a look at how we do that. That the variable cost associated with this particular department, based upon the data for the full year using the high-low method, is our variable cost is 17 cents a unit, and we also know our fixed cost amount to $17,525. So we can plug this information into our total cost equation, which is step 4. And if we take a look at that, our total cost equation is equal to our variable cost times our volume. That's a VC times V. Now, that should be in brackets because that calculation should be done first. So it's variable cost times volume. That's our total variable costs. Plus our fixed cost will then equal our total costs. So now I can create my equation for this entire department, if you will, with the units produced in total cost. And the equation is that I have 17 cents in variable cost times my volume, again that should be in brackets, plus $17,525 of fixed cost is going to equal my total cost. So I can plug in any number for V, volume, and I can come up with my total cost for this particular department based upon the high-low method. Okay, now let's take a look at another method of separating mixed costs, the variable portion and the fixed portion. And this is called the scatter diagram method. And here we see on the left-hand side, we see our total cost up between $0 and $40,000 and our volume in units between 0 and 80,000 units. Now, in this case, I'm going to then go out and identify all my costs at my different volume levels based upon my financial records. And I'm going to identify all my total production cost at my different levels of production, such as if I take a look at production volume of 20,000, it looks like I have about $20,000 in cost. If I look at the production level of 30,000, it looks like it's about 25. If I have production level of 40,000, it looks like it's right around 24,000. But this is basically the results of my actual production. So I post all these, and this is called a scatter diagram. Now I take a very straight ruler, and this is the unscientific method, but it's a fairly accurate method that one uses when they do the scatter diagram. I draw what I call the line of best fit. In other words, I try to create a line that would seem to represent a best fit through through all the items that are scattered, and you can see where I've created that line right here. So now that I've determined the line of best fit, what I do is I've drawn this line in here, and if you will notice that the line I've drawn in, it intersects zero volume at just about 16. Now this isn't extremely precise because this graph isn't too large, but it intersects at zero volume, it intersects at a total cost of $16,000. So we know our fixed costs are going to be equal to about $16,000. And the remainder above that is going to be basically variable cost. Now, in order to calculate the variable cost, we take where a line intersects, where we can come up with a really solid intersection. In this case, the best fit line intersects $24,000 at a volume of 40,000. So when we take a look at the line, we know that at 40,000 units, the total cost is equal to $24,000. Now it's a matter of calculating the slope, and it's very similar to the high-low method. We take our 24,000 in costs at that intersection right there. We compare it to the cost that intersect at zero volume, which happens to be $16,000. So when we compute the difference, it's 24,000 in cost minus 16,000 in cost at the zero volume. That means we had an $8,000 change in total costs. Now we're going to do the same analysis with volume. We take our 40,000 volume level that we got at the $24,000 cost, and we compare it to our zero volume level where we had our $16,000 of cost. So 40,000 volume versus zero volume means we had a 40,000 unit change in volume. So like we did in the high-low method, we take the $40,000 and we divide it into the $8,000 change in total cost. And in this case, the calculation comes up to 20 cents variable cost per unit of volume. So now we've determined our total cost. Also remember that we've also determined our total fixed cost of $16,000 because that's where our cost line intersects, our line of best fit intersects at zero volume. Okay, now step 5, we can create our cost equation, and again it's our variable cost times volume, and again, as I mentioned, that should be in brackets. So variable cost times volume, then plus our fixed cost equals our total cost, and that's at any level of volume. So our equation looks like this. It's 20 cents variable cost times whatever volume we decide to put in there, plus our $16,000 of fixed cost equal our total cost. And that's how we calculate variable cost and fixed cost utilizing a scatter diagram method. Now you may or may not have noticed, but the same data that I used in the scatter diagram I also utilized in the high-low method. You'll also note that, and we'll go over this in a few minutes in terms of a summary, each of these methods are producing somewhat different answers. So now we're going to go on to the third method, which is called the least squares method. Now we're going to address the least squares method, and here you can see a diagram, and all the cost volume data points have already been posted to it. As a matter of fact, it's off the same data that the scattergram data was calculated by. But in the case of the least squares method, what we do is we take all those green data points and we're going to put them into a program. Now, the least squares method is a statistical formula. It measures all the data points, I mean every single data point, and calculates a cost estimate line to create in effect, an imaginary line that minimizes the deviations between that imaginary line and all the data points. Now, in this particular case, it doesn't look highly complex, but what if you have hundreds or thousands of data points? Sometimes it's a good idea to use something like the least squares method. The least squares method is just again is a statistical formula, and it's part of what we call regression analysis. Now, one of the nice things about using the least squares method is it takes some of the guesswork out of the high-low method or the scattergram method. When I input all the data into the least squares method, what I'm going to do is get some very useful data out of the program. And this is the type of data you're going to see. Okay, you're going to see different values, A, B, X, and R. Now, those don't mean a lot. And so what I've decided to do here is I've kind of translated each of these variables into what may make a little bit more sense to you. The A is the fixed cost, okay, where the least squares method has identified the fixed cost. In effect, where that cost estimate line would theoretically intercept basically the volume at 0. Then we have B, which is called the dependent variable, and that for our purposes is a variable cost. Then we have X, the independent variable, and again for our purposes that can be interpreted as volume. Then we have an item called R, which is called the coefficient of determination. And this is actually a pretty interesting measure because it tells you how well that cost estimate line that it has created correlates with all those measured data points. And the coefficient of determination can be between -1 and 1. Now, what that means is that the higher the value, the better. In that, from a correlation standpoint, the higher the better. A value of 1 means there's a perfect correlation between that line of that estimated cost line and the data points. And of course, having a 1 is literally impossible. A value of 0 means there's absolutely no correlation of data whatsoever. A negative number, like a -1, means there's a perfect inverse correlation or a negative correlation. So the higher the value, typically when you're trying to get positively correlated material or a correlation, you want to see values that would be not necessarily 1, but something that is heading off towards 1. Okay, now let's take a look at the next slide. And this is an example of the least squares calculation method in action. Now, I'm not going to I'm not going to put data into the spreadsheet or anything else. We're just going to get some information, basically show you information that would have been derived from the spreadsheet. At the top, I just want to point out the fact is that these are all the data points, units produced and total cost, where we basically the information we're putting into that statistical program. And over on the right hand side you can see a graph depiction and how that statistical program is going to try to create this estimate line. Now, if you input all the data points into the least squares model, the calculation is going to give you the following information. A is going to be $16,947, which means A, remember, if we go back to the previous slide, that's our fixed cost. So what the least squares method is saying is that our fixed cost is $16,947. It also calculates out our variable cost. It calculates B being our variable cost, and that happens to be 19 cents per unit. So it calculates our variable cost to be 19 cents a unit. And then our R calculation, which it shouldn't be R2, it should simply say R, is 0.97, which tells us there's a very high degree of correlation. So the information has a high degree of, again, uh, correlation validity. Now, to determine the total cost within this department, we can go ahead and substitute these values into a cost formula. If you go back and take a look at the original cost formula that they show in the book regarding the least squares method, it's y equal a plus b times x. Or if you want to put it more into English, it means our total cost equals our total fixed costs, which is A, by the way, plus our variable cost per unit, which is B, times our volume, which is X. So again, if I were to refine this problem a little bit more, I would put brackets at the start of variable cost per unit and at the end of volume to ensure that calculation gets done first and separately. Now all we have to do is, if you plug in the values for A and B, variable cost and fixed cost, you get basically this following cost model, or this formula. It says for this particular company, the total cost is equal to our fixed cost, which now the least squares method says is $16,947 fixed cost, plus our variable cost of 19 cents per unit times volume. What you could do then is you could calculate the total cost for this particular department at any volume level. As an example, what I've done is I've now created a situation where what would be my total cost in my department at a volume level of 30,000? Well, the answer would be the $16,947 in fixed cost plus my 19-cent variable cost times my 30,000 volume. That means at a volume of 30,000, my total departmental costs are going to be $22,647. Now, I've shown you three different ways of estimating variable and fixed costs. We've used the scatter method, we've used the high and low, and the least regression. Now again, you can see that based upon the same data, these are all the calculations and how they came up with different numbers. If you take a look, and I'll start off with the scatter method, it showed a fixed cost of $16,000 and a variable cost of $20,000 or 20 cents per unit. And again, the scattergram was based upon a visual fit, basically an interpretation of the best fit based upon the scatter diagram. If I take, and again, that produces 16,020 cents per unit. Based upon the two measurement points, again, the high-low method gives me a fixed cost of $17,525 and variable cost equal to 17 cents per unit. The statistical technique, which is our least squares regression analysis, gives us a fixed cost of $16,947 and variable cost of 19 cents per unit. And again, all this data is based upon past data. Therefore, if we're using models to project the future, those models, no matter what you're using, could have errors in them because of things that could change in the future. The other thing is, no matter what we're using, whether it be a scatter diagram, basically a least squares regression method, the more data points that we can use, the better off we are. High-low only requires 2 data points. So you can see again that each different method gives a different answer. Which is the best method? Well, that kind of depends upon how sensitive you want your cost formula to be. You know, in a lot of cases when you're making some general estimates, the simple high-low method or scatter diagram can just be just as good, you know, as the least squares regression method. Okay, now let's do a couple observations regarding these cost models. First of all, cost models do not make decisions. Okay, managers make decisions. Cost models are decision aids. One of the other problems is that we're assuming a certain type of operating condition. I'm going to say a normal operating condition. Well, not all data can be based upon normal operating conditions. There could be anomalies out there that basically impacts the model. The other thing is right now our models are assuming basically that there are linear relationships exist. And in some cases, nonlinear relationships may exist, which can result in inaccurate modeling results at different volume levels. In other words, in some cases, the modeling for certain volumes could be right, and for other volumes, it could be incorrect. Model results, and this is something that's really important, and this goes back to managers making decisions. Model results should make sense. In other words, when you run the model and try a couple of different scenarios, is it coming out just about kind of what you thought it would? If it comes out something that looks completely different, you have to say, well, wait a minute, maybe this isn't the right model. Maybe this is not what I'm looking for. Even if something shows a high degree of correlation, but it gives you unusual results, you have to say, does this model really represent the situation? The other thing is we have to be cautioned about is that data used in developing cost estimates and models, it must be used on the same technology or process that we've assumed in the model. If we're going to do something that changes productivity, cost estimates, and so forth in the future, the models that we have built based upon those prior techniques basically wouldn't necessarily be applicable to what is happening with the changes we're making in the future. Okay, now one other area that we kind of need to talk about is that management accounting has been going in through a rather large metamorphosis, so to speak, over the last decade. If we take a look at this particular chart here, and again, this chart is out of the textbook, and we take a look at manufacturing costs between 0 and 100%. Back in the early 1900s, what we can see is direct materials composed maybe 15-20% of the cost of a product, but the vast majority of the cost of the product was the direct labor component. In other words, a lot of labor was being added, so the cost of that product contained, if we take a look at its composition, the majority of it contained the cost was direct labor and a fairly minor amount of manufacturing overhead. Well, what we see during over the years, we take it up through 1950 and through the year 2000, we see direct materials have increased a bit as a percentage, but the striking difference is the change in the swap of costs between direct labor and manufacturing overhead. Processes now, manufacturing processes and retail processes and so forth have become much labor intensive, and the manufacturing overhead, the automation part, is becoming much more intensive. So what you're seeing now is that there's an increasing de-emphasis on analyzing direct labor, and there's a much higher emphasis in basically analyzing manufacturing overhead. And again, okay, sorry about this. This is part of my slide. Direct materials are easily traceable to the product. And direct labor is easily traceable to the product because the product obviously incorporates the materials, and the direct labor actually is the labor that works on the product. So we can trace that to the product pretty well. But our problem is with manufacturing overhead. Again, that's that type of overhead that's essential to the production process, but we really can't trace it directly back to a production activity. So it's not easily traceable back to the product. So there's a great deal of work in management accounting going on, trying to come up with meaningful measures of being able to trace overhead type of costs back to products. Now, part of that is in what we call the manufacturing cost hierarchy. And what we see is that and this is kind of an inverse type of hierarchy here. We talk about unit level activities, batch level activities, product level activities, and facility level activities. And instead of utilizing one particular cost driver, one particular measure of volume now, what we're trying to do is we're trying to determine what are separate cost drivers for all of these activities, or is there only one cost driver? Are there many cost drivers for all of these different activities? So a separate cost driver is selected for each level of cost, or maybe a series of drivers. Now we're going to talk about what these particular activities are. And again, remember, we're not necessarily going to try to use the same cost driver to define each activity. We're going to use cost drivers that are unique and define that activity. Okay, now a unit level activity, that's an activity that is performed for each unit of product that's produced or sold. And examples of that is the cost of raw materials, the cost of cutting a component, the cost of a box to package, cereal, sales commissions, the cost of paintbrushes used by a painting company to paint an office building. These are at the unit level. Okay, now the next level is we go up to the batch level. And this is an activity performed for a batch of product or sold. So it's a batch of what we were just talking about, units. Okay, examples would be cost of processing batches of sales orders, cost of tracking work orders, cost of equipment setup, the cost of moving a batch between workstations, the cost of inspecting batches. We move up a further level of activity, and now we have product level activity, and that's an activity performed to support the production of each different type of product. And examples of that would be the cost of our production development, the cost of specialized equipment to produce that product, and the cost of maintaining that specialized product. And obviously these are examples. These are not limited to these items. And then the last level activity is going to be facility level activity, and that's the activity performed to maintain general manufacturing capabilities at the facility level. Examples would be cost of maintaining factory building and grounds, the cost of the real properties from where the factory is built, the cost of non-specialized equipment that services all products, the cost of our general advertising, and the cost of a factory supervisor or supervisors. So that gives us kind of an overall exposure to these different type of activities. And again, we're going to need absolutely different cost drivers that define these activities. As a matter of fact, multiple cost drivers within those activities. So that's the end of our presentation, and thank you for your time, guys.